Welcome to Math 1324. This is section 2.5 and we are looking at exponential functions. Now, what do they look like? Well, an exponential function looks like f of x is b raised to the exponent of the x. Now notice what's fixed here and what's the one that's changing. The variable is up here as an exponent. The b is a fixed constant, b for base. So b for base raised to the exponent, which is the variable x. Now, the b's that we can pick here are not any possible real number. The b can only be specific values. B can be a number bigger than 1, could be a decimal, could be 101.3, any number bigger than 1. It could also be a fraction between 0 and 1. So you might be saying, okay, it's all of those things. What can't it be? Well, b can't be 0. B can't be 1, and b can't be negative. So I could have f of x is 3 to the x, where b is 3. I could have g of x is 1/5 to the x, where b is 1/5. I could even have h of x being e to the x. They're saying, what is this e thing? Well, e is a number. It's a famous number like pi. And e is about 2.812, and it keeps on going. It should be on your calculator or your phone calculator somewhere, and it should look like a small e to the x. Not a capital E, but a small e to the x. Now, what do the exponential functions look like? Well, they all look about the same. If the b is bigger than 1, what was b again? B is our base. So we have f of x is b to the x, and if the b is bigger than 1, it looks like this shape. Grows quickly as it goes to the right, crosses at 0, 1, and on the left it shrinks down toward the x-axis. It never touches, so it's shrinking down toward y equals 0, which is the horizontal asymptote. The domain is all possible real numbers. So again, it has this shape of growing and pinching off for any b bigger than 1. If the b is our fraction between 0 and 1, it has a similar shape, but it's reversed. What's in common? They both cross at 0, 1. When b is our fraction between 0 and 1, it grows on the left and it shrinks on the right. So again, which shape simply depends upon how big b is. Bigger than 1 or between 0 and 1. So here's my basic shape of f of x is 2 to the x. Crosses at 0, 1, pinches off to y equals 0. What about if I add 1 on to the end? Well, we've seen this before, that is a shift up or down. And in this case, it's an up. So what goes up? Well, 0, 1 goes up by 1, making it 0, 2. But also where it pinches off to goes up as well. Okay, so it looks like that, and it's getting close to y equals 1. What about if instead of adding 1 on the outside, I add 1 here with the exponent? Then that means it's going to be a shift left or right. X plus 1 is 0, so x is minus 1. So the whole graph shifts left by 1. So this point, which was 0, 1, moves over by 1. That's why it's now sitting here at minus 1, 1. Where it's pinching off to doesn't change. We're just sliding to the left. There's no move up or down. All right, so looking at the homework, let's see. In question 1, they wanted us to figure out f of x is 3 to the x, and the interval is minus 2 to 2. So, since b is 3 and 3 is clearly bigger than 1, the graph will grow to the right, pinch off on the left to y equals 0, crosses at 0, 1. So I made a table here just so we could see these values. If you plug in negative 2, 3 to the minus 2 is 1 over 3 squared, which is 1/9. So here we are at minus 2 1/9. Plug in minus 1. 3 to the minus 1 is 1 over 3. Plug in 0. Something to the 0 power is 1. Plug in 1. 3 to the 1 is 3. Plug in 2. 3 squared is 9. So there's my graph for what this guy looks like. And so which one does it match with? Well, let's see. Well, clearly not C. That's a quadratic. Doesn't look like that. Let's see. This one is going the wrong way in terms of growing and shrinking. So there's only two possibilities, B and D. But remember, it crossed at a height of 1. And right there is the height of 1. See, this one is crossing, I don't know where it's crossing, but it's certainly not crossing at 1. Let's see, question 2 here. What's different is our B is 1/4. And yes, this particular B is clearly between 0 and 1. So the graph would go the other way. Well, if you plug in minus 2, that's 1/4 to the minus 2, which is 1 over a 4th squared. So that's 1 over a 16th. This fraction flips to give you 16. Negative 1, 4 to the minus 1 is 1 over 1/4. The 1/4 flips to give me a 4. And so you can see these particular points. Plug in 0, you still get 1, and so on. So the question is, which graph does it match? Let's see. Well, B and C are both quadratics, so not those. This goes the wrong way, so the only one left is D. And that does look about like what it's supposed to do. Is it crossing at 1? Well, yes, because these markings are going up by 5. So 5, 10, 15, 20, 25. All right, so let's see. We have f of x is 6 to the x. So that's going to look like the following because b is 6. So what about this 6 to the x plus 7? Well, let's see. What was the difference between 6 to the x plus 7 and 6 raised to the x plus 7? When it's out on the end, it's up by 7. When it's here, let's see, x plus 7 is 0, so minus 7, so left by 7. So take your normal graph, drag everything to the left by 7. So 0, 1 shifts way over to minus 7, 1. So what went on is we shifted to the left by 7. Graph is shifted 7 units to the left. Yep, that's what happened. All right, what about this e to the x minus 7? Well, here's our normal e to the x, crossing at 1, growing and shrinking to y equals 0. Let's see, minus 7 on the end is an up or down. In this case, it's down. So, what's going to go down? Well, this point will go down by 7. It's already up at 1, so 1 and down by 7 takes me to minus 6. If this is shrinking to y equals 0, it's going to shrink to y equals minus 7. So, down by 7. Let's see. Down. Shifted 7 units down. All right, in question 5, we get something different. And that is, if I have the situation of two bases match, then the exponents must be equal. All right, so in this problem, problem 5, notice the two bases are both 9. They match. Therefore, the only way this can be true is if the exponents are equal. So that's just a simple linear problem to solve. And so move the 4, 10x plus 4x is 14x, 2 plus 1 is 3. And then divide both sides by 14. Question 6. Well, let's see, looking here at question 6, again, I have the situation of the same base. Therefore, the exponent parts must be equal. Well, let's see, if I move everything to the right, I'll have a positive x squared, a minus 7x plus 12. Is it factorable? Yes. Let's see. Minus 4 minus 3 multiplies to give me a minus 12, yet adds to give me a minus 7. So set each part equal to 0, and I get answers of 4 and 3. Not too bad. Okay. What about this case? Let's see. In this case, we need a fact, and that is if a to the m equals b to the m. You say, didn't we have something just like that? Yes. What the fact is telling me here is if the exponents are the same, then the insides must be equal. Now, I have a little star here because we're going to see in a moment that this is true, but we need a modification when the exponent is an even number. But in this case, the exponent is a 3. They match. Now you might be tempted to say, okay, the insides match. Well, the problem is this. The right-hand side, the whole thing is not cubed. Only the x is the thing that's cubed. But if you think about it for a moment, 27 is 3 times 3 times 3. So I can rewrite this 27x cubed as 3x, that thing cubed. Now, since the exponents are the same, and I have something cubed equals something cubed, then the inside parts must match. Alright, so in that case I simply solve 4x minus 3x is x, and I move the 12 and I get x is minus 12. Alright, question 8. Now question 8, you might think, okay, great. I've got both of these guys are raised to the fourth power. Yeah, that's a good thing. The bases or the exponents do match. They both are 4. The problem is that 4 is an even number. Now, why is that a problem? Well, because minus 2 to the fourth, minus 2 times minus 2 times minus 2 times minus 2 is a positive 16. And so is 2 to the fourth. So 2 to the fourth is also 16. So minus 2 to the fourth is the same as 2 to the fourth. And the insides are not equal, but they're almost equal. They differ by a minus. So what that means for us is the following. We have the same exponent, it's even. Therefore, we have 2 problems to solve. The first is inside parts are exactly equal. Okay, so move the x, move the 9, and I get 5x is minus 5, or x is minus 1. But as we just saw, they could also differ by a negative. Therefore, inside part 6x plus 9 could be equal to the negative of the thing in the right hand side. Alright, so if you now distribute the x, alright, get the x's together, numbers together, 6x plus x is a 7x, minus 4 minus 9 is a minus 13. So x is a minus 13 sevenths. So again, we got into this trouble because the exponents matched, which was good, but it was an even number. And when it's even, you're going to have 2 separate problems to solve. All right, our final topic here is about banking. So, in banking, capital P is for principal, which is the amount of money we're going to put in the bank right now, or the amount we're going to invest now. It's going to sit in the bank. It's going to earn interest, and then we're going to get an amount A to come out at a future time. T in our problem is time, and this is always in years. Now, if they happen to give you the time in months or days, we're going to see in chapter 3 that we need to convert it to years. But for now, for this problem, they gave us the time in years. R is the annual interest rate, and it's a decimal number. N is often called the number of compounding periods, and it's how often the interest is calculated and added back to the principal. If it's annual, N is 1, quarterly, N is 4, monthly 12, weekly, N is 52. Daily, N is 365. In chapter 3, we'll see that sometimes bankers use daily as N equals 360. But that'll be clear in the problem if they want us to do that. If we have a fixed number of compounding periods, so here's this formula. This formula is if we have a fixed number of how often the interest is calculated. This is my formula. Rate as a decimal divided by N. N also appears multiplied by the time. Now, if you let the number of compounding periods run to infinity, which means we have continuous compounding. Then we have a new formula. And to find the amount of money at a future time, you take the principal times e raised to the rate times time. So on your calculator or phone, you need to look for an e to the x key. Sometimes it's on a key, sometimes it's above a key, and you would need to do shift. All right, so in our problem, we have P is 10,000. It's going to stay there 13 years. Rate is 3.15%. How do you get it to a decimal? Divide by 100. And so you see I plugged everything in. Now you start this by first getting the exponent on e. So 13, the amount of time, times your rate is a decimal, and I got 0.4095. Take e, raise it to that number. Now, don't write it down, because as soon as you write it down, you will have rounded it. You want to do the rounding at the very end. Alright, so we're going to calculate this number first, and while it's on your display window, multiply it by 10,000. That's where I got $15,060 and all these decimals. But we're rounding it to the nearest cent. So let's see, here's 64. The thing after the 4 is a 5. Therefore, drop this stuff and round this up by 1 to give us the amount we would have after 13 years. So good luck here in this particular section on exponential functions.